So, we have looked at what causes balance to be maintained or what causes loss of balance basically. So, if the line through the center of mass, the vertical line through the center of mass falls outside the base of support, then the body starts falling. So, today we will look at some strategies you can use to recover balance. So, if you are losing balance, how do we recover that balance, and we will look at the mechanics of it and see how to do that. So, once toppling has begun, how do we stop it? Okay. So, because we all do that, every time we lose balance we do not necessarily fall, you can recover your balance up to a point. So, we will look at what that is. So, here let us say you have, we will approximate the human, okay, and say the person is losing balance and falling because of this W falling outside the base of support. Okay. And if you look at the distance, perpendicular distance from the edge of the foot, then that, let us say that is d, then the toppling moment is essentially W into d, okay, at a particular instant. The problem is d will keep increasing as you are falling, okay, d keeps increasing once there is a disturbance that causes you to fall. So, this toppling moment, so when you have a moment, essentially its job is to increase the angular momentum of the system. So, this moment is responsible for increasing the angular momentum of the system. About the point of rotation, which is the edge of the foot.
Yesterday when we were looking at how much inclination that will take, is that the maximum value upper limit of the inclination?
Yes, beyond which you are going to fall. So, the question was yesterday when we looked at the balance of this person, right, we said what is the inclination after which the person is going to start toppling. So, yes, so beyond that angle, that is when this starts happening, the toppling starts to happen. Okay. So, we need some way of opposing this external moment in order to recover balance. And really in the absence of any external, so I could hold on to something and that could provide me, so if somebody pushes me and I am near a wall, I could just push on the wall and that can help me straighten myself. I do not have that luxury. So, I have to figure out what I can do with my body to try to, with the internal muscle forces that I can exert, what can I do to recover this balance? What movements can I initiate? What can I, with this multi-segmented system that I have, to try to recover the balance. So, that is the problem we are going to look at today. So, if you look at this in terms of the angular impulse. So, because your moment, okay, let us just look at it, the angular impulse equals the change in the angular momentum, because the moment equals the rate of change of the angular momentum. So, this means integral of w into d dt equals whatever is the moment of inertia of the system about that point, omega final minus omega initial. So, I is the moment of inertia of the body about an axis through the foot. So, since this d is going to be increasing very quickly, you can only recover balance if you act very quickly. Okay. So, beyond a point there is really not much you can do. So, let us see, if the body has a fixed configuration like this, okay, where you think of the body as like a solid cylinder, then there is really not much you can do. You start toppling like that, you are just going to fall unless there is some external intervention. But fortunately, our body is not a single solid rigid body. We have all these segments that we can use to sort of transfer the gaining angular momentum, and that is what we are going to look at. So, if the body has a fixed configuration, nothing can be done, because there is no way of counteracting this increasing angular momentum. Can be done internally. Externally, you can always apply a moment to counteract the to recover balance by counteracting the toppling moment. So, let us look at, now instead of just the body, now I have my arms. Okay. I separate the body into a cylinder, okay, and I say my arms are like two wheels. I can approximate them as two rings, two wheels that are pivoted at the shoulder. So, I am modeling my body now as the rest of the body and the arms, which I can represent as two wheels. So, here if I look at now, let me write the angular momentum of this system. Okay. So, I have, let us say the initial angular velocity was 0, but now let me say that the body, the whole body has an angular velocity about this point about which you are toppling of omega b, and I am now rotating my arms about the shoulder with an omega a. Okay. So, I start doing this, I start rotating my arms in the same direction that I am toppling, you know, I am falling like this, but I start rotating my arms. Of course, we are assuming here that you can do a full 360 degrees in a plane, which is not really the case, but you know, for the purposes of modeling, let us assume you can do that. Okay, we are assuming this is a wheel. So, approximate the body as a cylinder plus with axis at the shoulder. So, the body has omega b, arms are rotated. So, if the body has a clockwise velocity omega b, the arms are being rotated at omega a, also in the clockwise direction. So, this is we are talking about the frontal plane. So, you can see here this color and this color. So, you lift one arm and then you start rotating. You see these two. So, if this is one, this is also one. The colors kind of show that, but yeah, that is one. Then this is 2, this is 2, this is 3, this is 3. So, that is the relative location of the arms that you are seeing 1, 1, 2, 2 and 3, 3. So, now if we look at the total instantaneous angular momentum of the system, of the wheel plus body system about this axis through the foot. So, this is my A, okay, about A, axis through the foot, then I can write this angular momentum equals. So, I have the, let us say this is the, this is MB, okay, and the mass of the arms is MA. Let me just call each one MA by 2. Arms, the arms are approximated as wheels. Mass of body equals MB, and let us say its moment of inertia about the center of mass is IB, and similarly for, and let us say this is located from that point A, this is located at a distance R1, and then from the center to the center of mass of the body is R2. Okay. So, now I can write the angular momentum, the instantaneous, the total angular momentum of this system is, I have IB, okay, angular momentum of the body about its center of mass, plus using the parallel axis theorem MB R1 square, okay. This is rotating with omega b, okay. In addition, I have the arms, I am approximating them as wheels. So, I am saying, or rings, the center of mass is at the shoulder. Okay. So, I have m a r1 plus r2 square into omega b, again that the whole it is rotating with the body. In addition, I have I a omega a, angular momentum due to the arms rotating about the shoulder joint. Okay. So, these are the 3 components of this. Okay. Omega b I do not have control over, because yes.
This omega b which will be introduced, this is after the push, right? In this situation when it's starting.
At that instant,
Yeah.
the body is toppling.
So in that case, all the entire body, there is no external movement that will generate that, right? So there will be an equal.
There is
and
an
opposite.
external moment. The external moment is because
Yeah.
the weight has come out of the base of support, and now the body is tipping over the edge of the foot.
Yeah. So, but the movement generated due to arms, that there will be an equal and opposite movement on the body, the other body parts, the entire body separated from.
Okay, we are not looking. We are looking at angular momentum,
Yeah.
right?
So there should be an equal and opposite angular momentum generated at the other hinge, at the hinge as well, right?
That would be an internal. You are talking about. You are saying the angular momentum generated by this arm.
Yeah.
Yes, would be
If the arm is generating some x momentum,
right.
that then the place where.
So
it's
okay, let's be clear about the moment will be counteracted by a reaction moment.
Yeah.
The momentum is due to the motion. We are looking at angular momentum. Is the difference clear? Okay. A force would be counteracted by an internal force of the same acting on the other body. The motion, we are talking about the angular momentum, which is because of the motion, okay, which is equal to Ia omega A. Okay.
When you're taking angular momentum, you're taking it about point A.
Yes.
So for parallel axis theorem, it won't be R1, right? It will be something else. Are you approximating it to
I am taking R1 as the perpendicular distance from that point to that.
we should take it from the point A to M till M, right?
Point, I am taking the perpendicular, yeah, I am taking this. So, this is, I am taking about an axis that is passing through point A. Oh, you are saying it should be this distance. Line joining MB and A. Okay, okay, okay. I see what you're I see what you're saying. So if this were directly below MB, then R1 would be the same as that distance. Okay, fine. Yeah, it would be R1 should actually be this. You're right. Okay, but let's just approximate it here to be this distance.
And many into R1 plus R2 shouldn't be omega plus omega A.
This one? No, omega A is the angular velocity about the wheel is, the arms are rotating about that center, but the arms are also part of the whole body, and that is what this contribution is, and that part is rotating with omega B. Okay, the wheels themselves. So it's like this. If you just think of a rod, okay, with a wheel attached to it. Okay, the wheel is rotating at omega A. but the rod is rotating at omega b about this point. Okay. So, that is, so now this angular momentum of this system is because of WD. Okay. So, this is equal to, so if this is the final angular momentum, let us say it starts, this is integral WD dt. Okay. If this is the at a particular 0 to t WD dt. Then what happens is, now you do not have control over omega b, okay, but you do have control over omega a. Okay. So, this, if I start increasing omega, so this is sort of the same, okay. This is one quantity which is influenced only by W and D. Okay. If I take a snapshot, then this is going to remain the same, but I can play with the contribution. So, if I start increasing omega A, then omega B has to start reducing to keep this total instantaneous angular momentum the same. And in fact, I have to keep increasing omega A such that, because D is constantly increasing. So, I have to, if I have to write myself, then I actually have to increase omega A, so that omega B will become 0 when all the angular momentum goes to omega A. But even then there is a moment, and I actually now have to increase it even further to sort of go back. Okay. It is a very instantaneous, we are talking about something where you have to do it very quickly. But if you see, even when you push someone, right, instinctively your arms go up, instinctively you start rotating your arms in that direction, and that is kind of the way we try to regain that balance. There are other strategies, because your body has multiple segments. Another thing that we do is at the hip, someone pushes you, you immediately flex your trunk, right. If you push somebody suddenly, right, and they are going to fall forward, the instinctive reaction is try to flex at the hip, so that you are transferring that momentum to another segment that could actually help you, right. So, when you do that, now I am actually moving my CG, I start moving my CG backwards. So, the chances of my righting myself, preventing myself from falling increase. So, that is what we are, with this, because of the multi-segmented nature of the body, we are able to do that. This is a very simple model that kind of explains how we can do that. But so essentially what you are doing is, this external moment is increasing the rotational kinetic energy of the system, and you are doing internal muscular work to counteract that increase. So, you have to start doing more work in order to be able to straighten yourself back up. Okay. So, that is this I mentioned in the references, right. This book by Arthur Chapman has some interesting examples like this, but I like to do a few of these, so you get an idea of I think it is called Biomechanical Analysis of Fundamental Human Movements. I think I mentioned it in the I had the references that day. Yeah, this book, Arthur Chapman's book, has this and some other interesting examples of okay. Same analysis applies to the, you can do it for the losing balance in the sagittal plane as well. So, here again, so the lesson from this is, if you start to fall forward, then you start rotating, it's sort of counterintuitive. You think that you are going to try to rotate your arms in the opposite direction to try to go back. But what you are actually doing is not trying to provide a react, but you are trying to basically take that angular momentum into some other part. So, you start rotating in the same direction, you rotate your arms in the same direction as the direction in which you are falling. You are going to fall, because now that term actually becomes negative, you will probably just fall faster, yeah, right. So, there is of course a simple analysis of this, but it gives you some insight into how we do this. So, if the arms, the wheels are rotated faster and faster, until their angular momentum equals the total angular momentum of the system, the angular momentum of the remainder of the body becomes 0. But because the body is still leaning at that instant, you have to, that is not enough, just making it 0 is not enough, because it will just start falling forward, because you still have that unbalanced moment. Okay. So, so omega b will be instantaneously 0, but you have to prevent it from increasing further. Therefore, the arms must be rotated faster and faster. Till the rate of increase of their angular momentum will either equal or exceed the rate of increase of the So, essentially your shoulder muscles have to do the work to counteract the work done by gravity to do this. And if that work, the work of the shoulder muscles exceeds the work done by gravity, then you start straightening up. Okay. The body starts rotating in the. So, the other strategy of course is to use a hip flexor moment. So, if you have this guy falling, so assuming the rest of it is, you know, you are only assuming it as 2 segments, then if you start falling, you start bending, okay, and then you kind of assume a posture like this, and that will help you regain your balance. And the COM may actually become positioned within the base of support when you do that. If you combine this and the arms, then the chances increase of you. So, if without the person knowing, you push somebody, you will see instinctively that is the kind of righting mechanism we adopt. Be careful if you try it on somebody, and if somebody is, maybe you can do it, you know, now that you are aware of it, you can do it on one another, but yeah, do not do it on unsuspecting people, in case then I will get into trouble. So, okay. Similar kind of strategy when somebody is walking on a tightrope, right. So, this is, let us say they are walking on a tightrope. Say the person starts toppling in this direction, they start falling that way, then they should start rotating their arms in the same direction. Okay. This would be the arm motion. Now, challenge is here, you have a very small base, okay. It takes a lot of skill to walk on a tightrope. So, what they do is, many of them carry a heavy pole. Okay. What that does is, this pole has a high moment of inertia. So, even with a little omega, so with the arms, you know, there is only, you would have to start rotating them very fast to kind of absorb the angular momentum, to transfer the angular momentum to the arms. With the pole, because it has a high moment of inertia, you can give it a small angular velocity, and that will help to maintain your balance. Same principle that you do. Okay. So, then the important thing is, the motion is in the same direction, because what you are doing is transferring the angular momentum to the other moving segments. Now, in many cases, so in the body we have this we have the ability to use our muscles as actuators to apply forces and moments about the various joints. Now, we want to look at, in many cases we are also subject, as we have seen, we are subjected to a lot of external forces and moments. You know, for instance, how are we able to move our center of mass from one place to another? Like, you know, there is some interplay of external and internal forces happening that enables us to do this. Okay. So, in most cases, the external forces that act on the body what are they? What are the most common external forces that act on the body? As human beings, what are the external forces that we normally experience in most of our daily, in most of the activities that you do, walking, running, you know. Sorry? gravity. So, you have you have gravity. Okay. Gravity is something that is acting on us all the time. Friction, or what, I mean, what can you, friction comes from what? It comes from, it is essentially a, it is a ground reaction force. So, we also are subject to ground reaction forces. You have normal forces as well as frictional forces. Ground reaction forces are a very common external force acting on the body. Then due to fluids you can say air resistance, but in most cases we tend to ignore air resistance, because as compared to the other forces, unless it is in special situations where this is significant, we tend to ignore the effects of air resistance, because the other two are more dominant in the body. So, we want to look at, okay, what kind of forces. So, we, in many cases we want to be either propelled forward or we want something to brake our motion. Okay. So, those are the sort of and that is where these forces play a role. Like the air resistance is more of a braking force, okay. It is a resisting force, whereas gravity may be more of a propelling. It depends on the situation, it depends on the activity, but we will look at how these internal forces and the external forces kind of work together to make movements happen. Okay. So, when do you say it is a propelling force? When you want to move in a certain direction and the force is aiding that motion. Okay. Propelling force is when the movement happens in the same, or sorry, when the force is same direction as the force. And the braking forces, a propelling force, the acting force causes movement not necessarily in the same, but in the direction of, in the direction in which you want to go. Okay. In a let's, it is typically referred to as forward progression, direction of forward progression. So, if I am walking from point A to point B, then that is my forward progression is from A to B. A braking force, these are external forces that act opposite to the direction of progression. The ground reaction force, as its name implies, is a reaction force. Okay. There has to be some action that causes that reaction. So, the GRF is basically a reaction force of the ground. So, let us look at a simple case where you take let us call this a frictionless surface. I have two masses connected by something, okay, that can apply a force on these two masses. So, some actuator in between, okay, which can, so this would be like similar to your muscles. I have one segment, another segment, and you have a muscle that is capable of applying a force to each segment. Now, I can say that, so these are both internal forces, right. So, if I, let us say I say F1 is the force on mass M1, and F2 is the force on M2, then I have F1 equal to minus F2, okay, and the magnitude of F1 equal to the magnitude of F2 equal to F, okay. So, I have F1 plus F2 equal to 0. This is my Newton's third law, right, because those two. So, if I write this in terms of the change in linear momentum of these two bodies, I can write it as m1 delta b1 by delta t plus m2 delta b2 by delta t equal to 0. If V1 equal to V2 equal to 0 at t equal to 0, I start from rest, okay, and then I can write it in terms of displacement. I can write it as m1 delta r1, okay, whatever the change, plus m2 delta r2 equal to 0. Okay. So, what does this tell me? This tells me that the center of mass of the system does not move. Applying only internal forces cannot make me change the center of mass of my system. So, if I was not acted on by any external force, I can move my limbs all I want. Say I am suspended in a gravityless environment, unconnected to anything else. I can move my arms any which, I can move my limbs any which way I want, but I cannot change my center of mass. That's what this is telling me, right. So, we will continue with this, So, then how do we move? Because walking, running, a lot of the things that we do involves moving our center of mass from one place to another. So, how do we manage to do it? Okay. How do we use the external forces to help us move the center of mass?